This topic is about nitrogen compounds and a little bit of polymerization at the end as well. One of the key nitrogen compounds is something called an amine, and an amine is anything that has this group NH2 in it. They come as primary, secondary and tertiary, just like your alcohols come as primary, secondary and tertiary. So a primary one just has one alkyl group attached to it, whereas a secondary one has two alkyl groups attached to the nitrogen, and a tertiary one will have three alkyl groups attached to the nitrogen. If we have something called an aryl amine, this is where you've got the ring attached to an NH2, so you've got your benzene ring and then you've put an NH2 on there as well. You need to know how to prepare these amines, so the reactions that are used to create them. If we want an aliphatic amine, so a non-aromatic one, just a straight chain one like this one here, then you need to produce this by heating. So one of the conditions is heating. It needs to be in a sealed tube, another condition for this reaction. And the reactant that you need is excess ammonia, but it actually needs to be dissolved in ethanol. So in terms of your reaction conditions, remember those things. This is a two-step process, and what you do is, first of all, you make the salt of the amine and then react that with sodium hydroxide to make the actual amine. Make sure you know these reactants, make sure you know the conditions as well. If instead you're trying to make an aromatic amine, so one attached to a ring, then you need to do reduction of nitrobenzene. So you make your nitrobenzene by your nitration through electrophilic substitution that you should be familiar with the mechanism for, and then you add concentrated hydrochloric acid to that nitrobenzene, and you also need tin in there as well. And that's actually done by heating, and it's specifically heating under reflux, so where it's going to be evaporated, then condensed, then re-evaporated, recondensed, and this process goes on and on in reflux. You represent this by having your nitrated benzene, your nitrobenzene, and we show this here is our reducing agent. So that is represented by a H in square brackets, and what you'll get is your products are your aromatic amine, your ring amine, and you'll also get water. Again here you actually make the chloride salt first, and then you have to add sodium hydroxide as well, and then you can extract the amine from the reaction mixture by something called steam distillation. So distillation is where you heat it up and then condense it, but distillation, that process only happens once, whereas reflux, that evaporation and condensation is repeated. Your NH2 group can actually form hydrogen bonds, and so that means that they're going to interact with water molecules. Anything that has a short carbon chain, so this R part of your amine, anything with a short carbon chain will actually be miscible with water. It will mix with water, and what will happen when it mixes with water is that an alkaline solution will be formed, so you'll get the OH minus formed there. Just like with your carboxylic acids, as the carbon chain length increases, these amines become less soluble in water, they're less likely to dissolve in water. That means that other things as well, like phenylamine, so that's an amine attached to that C6H5 group attached to a benzene ring, is actually only slightly soluble, a little bit soluble. It will only dissolve a little bit because of that large carbon group, the C6H5. Other reactions that they do are actually acting like bases. So they'll react with an acid and a salt will be formed. So in this example here, you've got butyl ammonium chloride. Butyl from the alkyl part, and then ammonium chloride from the NH3 plus Cl minus. This means that actually you can dissolve your phenylamine in hydrochloric acid, and just like with your straight chain ones, your aliphatic ones, you get a salt produced. If you then react this salt with sodium hydroxide, you get the reverse reaction and can reform that phenylamine again. So this is a reversible reaction. Other reactions that you need to be aware of are the reaction with halogenoalkanes. So that is an alkane with a halogen attached to it. What will happen here is actually the lone pair on the nitrogen is going to attack an area of positive charge, and so it'll attack that slightly positive carbon in the halogenoalkane, and what will happen is that will form a secondary amine, and then if this reaction continues you'll form a tertiary amine. So you get attack from the lone pair on the nitrogen onto that slightly positive carbon there, which is attached to the bromine, and that can happen again where here in your secondary amine you still get the lone pair attacking that slightly positive carbon. We get a similar reaction with acid chlorides, so again the lone pair on the nitrogen is going to attack the slightly positive carbon. This time it's slightly positive because of the difference in electronegativity between the carbon and the oxygen. So if you have an acid chloride, then the amine is going to act as a nucleophile and you're going to form an acid amide. So this here where you have your CO bond and you also have an NH with whatever R groups it was on your original amide. One example of this, and a common example of this, is that you can make paracetamol. So from our 4-aminophenol, you're going to create paracetamol here. So the reaction that's happened is actually your NH2 here attacking this carbon, and that gives us the product over here where we have this group attached to your benzene ring, or to your phenol ring really, because it's got the OH on it. This topic also links in with what you might have done in your transition metals about bidentate ligands, and the lone pair of electrons on the nitrogen of your amine means that it can form these complex ions such as 1,2-diaminoethane, forming a complex with a transition metal. A really common exam question that comes up is one about the formation of azo dyes, and this is a several step process. So nitrobenzene with our NO2 group on is heated, so the conditions are it's heated, it's under reflux, and you need a tin catalyst as well as some concentrated HCl as our reducing agent. Remember we said we represent this reducing agent as our H inside the brackets. And what happens here is you'll actually get an NH3 plus group forming there, which can go on and react with OH minus, and that is what will form our aminobenzene. This aminobenzene then goes on to do a further reaction with HNO2. You need to know how the HNO2 is made. It's actually unstable, so it needs to be made from our hydrochloric acid and sodium nitrite. Then you need to make sure that your phenylamine, so this one here, phenylamine is dissolved in moderately concentrated hydrochloric acid, and it does need to be cooled to about 5 degrees Celsius. That's an important condition for this reaction. Your sodium nitrite is also cooled to 5 degrees Celsius and added slowly to the phenylamine and the acid in order for this reaction to happen and the HNO2 to be produced. It needs to be kept cool and kept below 10 degrees Celsius now, and that will allow the phenylamine, this one here, to react with the HNO2 to form benzene diazonium chloride, which is this molecule here, the C6H5 with an N2 attached to it, but you need to represent the N2 with those 3 bonds in between and that positive charge on it. You've also got the Cl minus there to make sure that this remains charge neutral overall. We said this is benzene diazonium chloride, so this is how we're going on to form a azo dye from the diazonium, and the diazonium is this group here, the N2. That benzene diazonium chloride is unstable, so actually you need to create straight away the next step in this reaction. And you take the cold solution of this and add it drop by drop to a cold solution of phenol in sodium hydroxide. And that should give you a yellow or orange precipitate of the actual azo dye that you're trying to create. So take your diazonium ion here, and it actually reacts with the phenoxide, so that's from your phenol, but it's to the O minus variation, and you get a link between the nitrogen here and this part of the ring. So it attaches opposite the OH, and this linkage here, this is known as our azo dye. As well as knowing about amines, you need to know about amides as well. Just be careful that you don't get the two muddled up. An amide is a derivative of a carboxylic acid, so it comes from a carboxylic acid, and it's actually where you've got the C double bond O NH2 group in it, rather than the amine, which is just the NH2. If we want to prepare an amide, so the reaction to synthesize an amide is by reacting an acyl chloride with concentrated ammonia. Happens at room temperature, and the observations that you'll make are that you make fumes of HCl, and you also get the solid amide being produced here. So the acyl chloride reacts with your concentrated ammonia to give you, in this case, ethan amide, because it's got 2 carbons in it, hence ethan amide. Your addition polymerization is where you build up a long chain molecule from much smaller molecules. The smaller ones are known as your monomers, and then the larger ones are known as your polymers. In your addition polymerization, you're adding together these monomers and you don't get any other products. However, in your condensation polymerization, you always make a small molecule such as water or HCl for every link that is made. In addition polymerization, you often make it from a carbon-carbon double bond. So, for example, if you had phenylethene, where the pH there represents the phenyl group, the C6H5 group, those would join together to make a chain where you have the repeating unit, where that's the carbon-carbon double bond that's turned into your carbon-carbon single bond, and that then continues to repeat as it's a long chain molecule. Your condensation polymerization, that's where you have bifunctional monomer molecules, where you have 2 different functional groups on your monomer molecules. Or you can have it where you have a diacid and a diol that will link together to make the functional group in your condensation polymer. So an example of condensation polymerization was where you make a polyester. And polyester is where you have the ester linkage, so the C double bond O with an O next to it, and you've formed that by using your carboxylic acid group and your alcohol group. So just like when you form a normal ester, but this time you're forming a repeating chain, and this chain goes on and on and on. In this example here, you've got a dicarboxylic acid and you've got a diol. So you've got 2 carboxylic acid groups and you've got 2 alcohol groups. Every time you form one of these ester linkages, you actually lose an H2O. So that's an H and an O from the carboxylic acid, and then just the H from your alcohol group. So you lose that H2O, and it's a condensation reaction. You can actually have it where you have the alcohol group and the carboxylic acid group on the same molecule. That does the same thing. It forms that ester linkage, the C double bond O with the O, but this time it's one end of your monomer joining to the other end of the same monomer. Again, the water comes from the OH in the carboxylic acid and the H in your alcohol group. These ester links can be slowly hydrolyzed by acids and can be more rapidly hydrolyzed by alkalis. When we say hydrolyzed, we mean they can be broken down, so they'll break back up into your original functional groups of the carboxylic acid and the alcohol. Your polyamides form in a similar way, but this time you need to have the acid group and you need to have your amine group. And so instead of the acid group and the alcohol group, we've got the acid group and the amine group. And this actually forms something called an amide link. It's very similar to your ester link, but you've got a C double bond O and an NH. So it's similar because you've still got the C double bond O, but you've got an NH instead of the other oxygen in your ester. This reaction can then carry on because you've still got the NH2 on the end of one molecule and you've got the COOH on the other end. And so you can then repeat this reaction, and that's how you form a longer chain. In this particular example, where you've got the 6 CH2 groups in between your 2 amine groups, and where you've got 4 CH2 groups in between your 2 carboxylic acids, this forms something called nylon 6,6. We call it 6 because there's 6 carbons in your carboxylic, your dicarboxylic, and there's 6 carbons in your diamine as well. The repeating unit here is your amide linkage in the centre, and then it would join up, the nitrogen would go onto the next carbon, and it would just repeat and form a polyamide. Another example you're expected to be familiar with is Kevlar. And Kevlar again has this amide linkage, and it's made up from a dicarboxylic with the benzene group in the centre. And then the other one is from a diamine with the benzene group in the centre. It's a really, really tough material, and it's often used in bulletproof vests. You do need to be able to draw these polymers and find repeat units. So you could be asked to take your monomers and describe what would happen in terms of those joining together to form your polymers. This also works here. We've got an acyl chloride, and that does a very similar thing and provides you with that ester linkage to make a polyester. So don't forget, that's another way that you can make your polyester. Your repeat units, look and see how many repeat units the question is asking you to give. If it asks you for 2 repeat units, make sure you have that C double bond O linkage represented right in the centre, and then that would actually kind of attach on to the one at the other end there, so show 2 lots of that repeated ester linkage. The questions are less likely to ask you to draw addition polymers, but just make sure you're still aware of how to do that in case they do ask. If you're asked to work out the monomer units from the polymer chains, then you've got to go backwards. If it's got an ester linkage in it, then that means it's obviously a polyester, so your groups that you should have as your functional groups on your monomers should be the carboxylic and the alcohol. However, if it's got an amide linkage, it's a polyamide, and you should be looking to create monomers that have a carboxylic and an amine group on them. If it's just a continuous carbon chain and it hasn't got an ester linkage or it hasn't got an amide linkage, then that's probably come about because of adding those monomers together, and so that must mean that there was originally a double bond between those carbons. Looking at a couple of examples here, you can see that you have got a C double bond O NH, so this is a polyamide, so you want to split it up into your COOH groups on the end here and your NH2, your amine groups on the end here as well. However, here you've got a repeated carbon chain. There isn't an ester linkage, there isn't an amide linkage, so that must have come from a carbon-carbon double bond. And if you think about splitting it up into the individual monomers, that's one monomer there, and you've got the next one here, the next one here, and so on and so forth. Just watch out for the different groups that you can have around that carbon-carbon double bond. If you have ethanol, where you've got the carbon-carbon double bond and the alcohol, then you're going to make polyethanol, and it's going to look like this. Whereas if you have 2 hydrogens and then you have this CONH2, then that is going to turn into polypropanamide instead. Because you have an alcohol group in this example and an amide group in this example here, then you can actually form hydrogen bonds, and so they'll interact with water. Polyethanol will actually dissolve in water and can be used in dissolving laundry bags. It can also be used for the detergent capsules that are around the liquid that you place in your washing machine or that you would put in your dishwasher perhaps. The polypropanamide doesn't actually dissolve, but it can absorb water molecules and become softer in water, so it's actually used to make soft contact lenses. Another nitrogen-based organic compound you're expected to know about is the group of amino acids. An amino acid is going to have an amine group, an NH2, and a carboxylic group, a CO2H as well. They have the general formula RCH-NH2COOH, where R represents a side chain, and your group of amino acids just has loads of different side chains, but always will have a CH, NH2, COOH. So if we look at the example of glycine, there's your COOH, there's your NH2, there's your CH, and then our side group is the R is just an H. In this example here, that's COOH, NH2, CH, and here the side group, the R, is CH3. Final example, cysteine, again, COOH, NH2, CH, and your side group is actually a CH2SH there. We describe these as alpha amino acids, and there's about 20 different ones that are found in nature, and they will combine to make up proteins, so they're like the building blocks of life. You need to know how they'll react. Just like your amines, your amino acids can react with acids, and they will actually act like a base in the reaction. So if you had the example here where the side chain is CH3CH2, that'll react with your acid H+, and you will form an NH3+ there instead, so it'll be attracted to that lone pair on the NH2. Opposite reaction is that because they have the carboxylic acid group as well, that carboxylic acid group can react with bases. So the COOH can react with an OH- to give you the CO-, the carboxylate, and it'll give you H2O as well. If you have a amino acid in solution, you actually lose the acidic hydrogen on the amino acid, so you lose the H from the COOH, and it'll actually attach itself and be attracted to the NH2, so it'll turn into NH3. Because you have that negative here and this positive here, we call this a zwitterion. It's got both a positive cation group and a negative anion group, and which ones will be formed depends on the pH of the solution in which they're dissolved. So if you have a low pH, so if you have something pH 1, pH 2, very acidic, then those acidic H pluses in your low pH solution will be attracted to the NH2, and you'll form the NH3 plus. If you have a much higher pH, something around pH 13, 14, a much more alkaline solution, then you will remove the H from the CO2H and just make COO-. If you've got a kind of middling pH, then both things will happen. So you'll have the CO2- and the NH3+, and that, as we said, is known as your zwitterion. We talked about forming polyamides, and your amino acids can actually do this reaction. So the carboxylic on one will join with the amine on the other, and you'll make an amide linkage. You'll start to make, if it carried on, it would be like a polyamide. And we just say that this is, you formed an amide, sometimes referred to as a peptide link. And you tend to show the amino acid with the unbonded NH2 on the left. So here your NH2 isn't bonded, and so that appears on the left hand side of your amide linkage or your peptide linkage. Like I say, we call it a peptide bond when it's amino acids specifically. And if you have more than two amino acids joining together, if you have several amino acids joining together, we say we form a polypeptide. And your proteins are actually made up of one or more polypeptide chains. So if you have a protein, you can break it down into the individual amino acids by hydrolyzing the protein using concentrated hydrochloric acid, and then you could separate those amino acids to identify them using chromatography. The amino acids are actually colourless, they don't have any colour, so you need to form a coloured product, and that material, that chemical that we add to it to form a coloured product is known as a locating agent. And the specific one that we use is something called ninhydrin, and if you spray your chromatography, your chromatogram with ninhydrin and then put it in the oven at about 100 degrees Celsius, then the amino acids will show up as purple spots that turn brown over time, and then you can identify the different amino acids. We can identify the different amino acids by something called the RF value, and the RF value is the distance moved by the compound from the starting line. So that would be from the starting line to your dot that represents the amino acid, divided by the distance moved by the solvent front, so how far the solvent has got up your chromatogram. And if you do the smaller one divided by the larger one, you get something called an RF value, and different amino acids will have different RF values.